when we have divided by 6, we have got 6 possible remainders, my dear children. R less than 6, greater than or equal to 0. Remainder will always be less than 6, but still 6 remainders, 0, 1, 2, 3, 4 and 5. Similarly, when I divide by 7, 7 possible remainders, 0 to 6. If I divide by 8, 8 possible remainders, 0 to 8. If I divide by 14, 14 possible remainders, 0 to 14. So now what you will be doing is that I have given you a small activity. Right now it will be seen on the screen. What question, what activity you have to do? You will just try it on your own. You will be dividing a few numbers by 8. So if you are dividing by 8, how many cases? Yes, you will have 8 possible cases wherein the remainder would be 0, 1, 2, 3, 4, 5, 6 or 7. Remainder cannot be 8 when you are dividing by 8 because remainder is always less than the divisor. When the divisor becomes 8, remainder will be less than 8, right? So it would be 8 remainders but starting from 0 till 7. Similarly, when you will be dividing by 11, you will check it out what happens. So you yourself understand this concept. A is equal to BQ plus R, where A is always greater than B. Q and R are the new set of integers, Q and R, such that this R is always less than B. This is our ideal Euclid's division lemma. It has got many applications, but the major 2 applications of ideal, first one is to find the HCF, highest common factor of given 2 integers, and second one is proving a particular form, this A is equal to BQ plus form. Right now, today we will first see this example, how to solve the sum when they are asking to prove a particular form, correct? Using the ideal. So what we'll do is that right now is that you will be seeing a question on the screen. This is the question from our exercise, first exercise, wherein they are telling us to prove that any odd positive integer is of the form 6q plus 1. I am writing it on my board over here. 6q plus 1, 6q plus 3, 6q plus 5. Now, see, you remember the Euclid's division lemma was for any integer. Right now, here they have still specified it further. They are calling it odd positive integer. Means they are specifically interested in the odd integers. Now, you know that integers are either odd or even. Right now, they are asking us about odd, and odd integer has to be of the form 6q plus 1, 6q plus 3, 6q plus 4. Now, very important, I will tell you this one method. You just observe. Later on, I will also send you the pic of this solution. But understand, whenever, now understand it point wise, whatever I am saying, okay? And you will learn it in this way only, because that is a standard way. It's a way of correctly representing the answer. Whenever a question comes like this, proving a form of 6q plus 1, 6q plus 3, 6q plus 5, proving a form of 4q plus 1, 4q plus 3, 2q plus 1, 9m, 3m, anything. When a form is asked to be proved, the answer, the solution will always start with a sentence. Let A be any positive integer divided by 6. Because see, it is BQ plus R. So here B is 6. The divisor becomes 6. If at all it would have been of the form 4m plus 1. Suppose they would have asked us prove 4m plus 1, 4m plus 2. Then A is equal to BQ plus R. So now the B takes the value as 4. In this case, B has taken the value as 6. So how am I going to write? Let A be any positive integer divided by 6 to get a remainder R. Now, just now we had seen in the earlier case, when we divide by 6, R will take how many possible values? Yes, 6 possible values. Which are those? 0, 1, 2, 3, 4 and 5. So that's what I am going to write. So we are always going to start this answer with this statement only, compulsory. Let a be any positive integer divided by. Now if the form is 6 cube, so divided by 6. As I told you, if the form would have been 4m plus 1, 4m plus 2, something like that, what I would have said? Let a be any positive integer divided by 4. If the form was 2m, 2m divided by 2. If the form was 9m plus 1, 9m plus 3, 9m plus 8 divided by 9. If I am dividing by 6, I get 6 remainders. If I divide by 4, I will get 4 remainders. Which are those? 0, 1, 2, 3. When I divide by 2, I will get 2 remainders. 0, 1. When I divide by 9, I will get 9 remainders, and so on. So the first statement is clear. Correct? And which are the possible 6 cases? Yes. A is equal to 6q plus 0. That is 6q, you can say. A is equal to 6q plus 1. A is equal to 6q plus 2. A is equal to 6q plus 3. A is equal to 6q plus 4. And finally A is equal to 6q plus 5. Let us check it for the same example what we had taken. 12. We had divided 12, right? So 12 is equal to, so the example what we had taken, it was from 12 to 18 we had checked. See, so 6 into 2 plus 0, so 6q plus 0, 6q plus 1 plus 2 plus 3 plus 4 plus 5. 4 into it becomes again 6q plus 0. Now see, this is just an example I am showing you, right? Now they were asking us about odd positive integer. Just to make it understand clear, you can see that 12, 14, 16 are even. Correct? And we are interested in the odd numbers. See, this was the odd number. 13, can you check it? 15 and 17. What is this form? 6q plus 1. 6q plus 3. 6q plus 5. This is what they have asked us. 6q plus 1. 6q plus 3. 6q plus 5. And what did we know that? This 6q plus 0 plus 2 and plus 4 were 12, 14 and 16, because 6q is already an even number. Correct? Even plus 0 is even. 6q every time is even. Even plus odd is odd. Even plus even is even. You can check it. Even plus even is even. Even plus odd is odd. Even plus even is even. Even plus odd is odd. Hence, even plus even is even. Even plus odd is odd. Even plus even is even. Even plus even is even. Right? So that's what we have said, that this 1, 2 and 3. Can you see that this A, this 6q plus 0, 6q plus 2 and 6q plus 4 have become even, hence invalid, because they have asked us odd integer is of the form 6q plus 1, 6q plus 3 or 6. So now what we are going to write is that. So this is what we have already written. We have already written that let A be any positive integer. That is going to be our common. We are going to learn it by heart. Let A be any positive integer divided by so and so to get the remainder so and so. So if it is divided by 6, we are going to get 6 possible. I am repeating it again and again so that it comes fit into your brains. So let A be any positive. So what am I going to write after this step is that we'll write but. This is a very important statement. 6q plus 2 and 6q plus 4 are what? What are these numbers we had seen just now? Even plus even? Even. We had written this is even and even, and hence invalid because they have asked us odd integers. So 6q plus 2 and 6q plus 4 are even, hence invalid. Correct? These numbers are even, hence invalid. So the odd numbers, whichever odd numbers are there, they will either be of the form 6q plus 1 or 6q plus 3 or 6q plus 5. What you can do is that you can check out any random odd integer. And if you divide it by 6, you will get either this form or this form or this form. That you will be doing as an activity. So my final statement here, but 6q plus 2 and 6q plus 4 are even, hence invalid. Therefore, any odd, this is a question statement, odd positive integer is of the form. Which form? Yes, tell me now. These three have become invalid. So this is invalid. This is invalid. This is in what remains? 6q plus 1, 6q plus 3, 6q plus 5. And this is what they had asked, is of the form 6q plus 1, 6q plus 3 or 6q plus 5. Hence proved. Always we have hence proved ourselves. So this is how we have proved ourselves, right? Now just see what they had asked us. They had asked us to prove any odd positive integer. If they would have asked us any even positive integer, now you already have the answer, right? What will be the even positive integer? हे 3 सोडून हे 3 काय आहेत? ऑड आहेत. म्हणजे राहिले 3 कोण आहेत? आपल्याला ऑलरेडी माहित आहे. मग आपण काय म्हणणार त्या केस मध्ये? 6q plus 1 plus 3 and plus 5 are odd. इथे कसं म्हटलं? इवन हेन्स इनव्हॅलिड. मग काय म्हणायचं? आर ऑड हेन्स इनव्हॅलिड. Therefore, any even number is of the form 6q, 6q plus 2 or 6q plus 4. हे झालं एक. Similarly, now if they might have asked us, prove that. Now see, I'm adding a condition. Now they had asked only for odd. Now I'm adding a condition, which is again a question for us. Suppose they ask me, prove that square of any integer. Okay. Now which any integer? Which is our any integer? A. Let A be any integer. Means they are asking the square of A. So let us see what is the question. So we have to, now in the other example, there was square of any integer to be of the form 3m or 3m plus 1, right? You will be solving the sum, right? I'll be sharing a pic of this. You can copy it down in your notebooks and try to solve it on your own. So here, this question you will be solving on your own. I'm not going to send you the pic, but I will show it to you over here. Now you tell me what? Which form do you want? 3m or 3m plus 1, means this 6 gets replaced by 3m. Same thing. So this is no third form, only two forms they are asking us. 3m or 3m plus 1. And when will we get a form of 3m? When the divisor will be 3. So how does our answer start? Yes, the statement, the by-hearted statement. Let A be any positive integer divided by 3 to get the remainder r is equal to 0, 1, 2. Correct? So A can be written in the how many ways now? In the following 3 ways, because now A is divided by 3. So what are we going to get? A is equal to 3q plus 0, that is 3q, or 3q plus 1 or 3q plus 2. These are the only 3 forms that A can take. A becomes 3q, or A is equal to 3q plus 1, or A is equal to 3q plus 2. But in the earlier case, they had asked us only odd. Now they are asking us square of any integer. Mind where it is? Square. The important word over here is square. Just the important word over there was odd. Now A is of this form. We want to check what will be the square of A. Square of any integer. And A is any integer. Means what we have to do now? Squaring all the 3 numbers. We'll check what happens on squaring A. Very quickly, let me do case 1, case 2 and case 3. Very fast. So let me write here case 1. A is equal to 3q. Therefore, A square would be 3q whole square. Correct? What is 3 square? 9q square. And we want the form what? 3 into m, where m is some integer. They are saying where m is some integer. Okay. This is the condition what they have given us, where m is some integer, correct? So now this 9q square, can I write it as 3 into 3 into q square? Am I right? 3 is a 9, 9 and into q square. And now see what? Q was already an integer. We knew that A, B, Q, R, all four are integers. So integer square, again an integer. Integer into 3, integer. So this entire thing can now be replaced as m. 3 into m, where m is some integer. So the first case, a square became 3m. Let us check case 2. What would be the case 2? Case 2 is a is equal to 3q plus 1. 3q plus 1. So a square would be 3q plus 1 the whole square. How do we open the bracket? A square plus 2ab plus b square. Let me open it. Is equal to a plus b the whole square. A square plus 2ab plus b square, which gives me 9q square plus 6q plus 1. Again, from these two, 3 is common. 3 common, what remains? 3q square plus 2q plus 1. Here, where m is equal to 3q square, some integer. Let me bring this bracket over here. You have got a is equal to 3 into 3q square plus 2q plus 1. And this entire thing, see, q square is integer, integer into 3, integer, integer plus integer, integer. This entire bracket becomes an integer. So a is equal to 3 into some integer m plus 1, where what? M is equal to 3q square plus 2q. Similarly, you will prove for case 3. Case 3, children, you can do it on your own. A is equal to 3q plus 2. 3q plus 2, so a square would be 3q plus 2 the whole square. So what do I get? 3q plus 2 the whole square. I get 9q square plus 12. 12q plus 4. After applying a square plus 2ab plus b square. Now I don't want plus 4. I want either 3m or 3m plus 1. Very intelligently, we'll write this like this. 9q square plus 12q plus 3 plus 1. From all this, 3 is common. What remains? 3q square plus 4q plus 1, and this plus 1 is outside the bracket. That is 3m plus 1. Hence proved. First case, case 1, the square was 3m. Case 2, the square was 3m plus 1. A square was 3m plus 1. And case 3, again the square was 3m plus 1. Ultimately, square of any integer a square here and a square here. A square is either 3m or 3m plus 1 or 3m plus 1. Means square is either 3m or square is 3m plus 1. This is how we will be solving this. But in short, let me revise it. Whenever you have to prove a form 3m, 4m, 6m, 6q, 2q, we will start, yes, let a be any positive integer divided by 3, divided by 6, divided by 4, whatever it is, to get the remainder r. If it is divided by 3, 3 possible remainders, 0, 1, 2, divided by 6, 6 possible remainders. And then take the required cases. If squaring is asked, ask prove for square. Cubing is asked, prove for cube. I will be giving you 1 or 2 more questions. You will try it on your own. That's all for this session. Thank you. We'll meet in our next session tomorrow. Thank you.